Recording in progress.
Pam, good morning.
Good morning.
How are you?
I'm good. How are you?
Is that on the campus?
Yeah, all the tables in the sewer hall were taken, so I just sat outside today.
Oh, it looks nice. Is it still kind of deserted there?
There's actually a lot of people here today.
Oh.
There was just a bunch of people walking by. I think they all got to class though.
Yeah, I guess everything started at 9:30.
Yeah, I think so.
It was probably still only like half as crowded as it normally is.
Yeah, I'm not sure. I've never seen it fully crowded.
Oh, that's true. I mean, if you've been a student during the pandemic, you've never seen it at full capacity.
Yeah, this is my full capacity.
Can you believe there's actually,
relative to what I've seen,
there's actually 16,000 students?
That's wild. Wow.
I know. But I'm not there all at once, obviously. But like when I was going to my university at UC San Diego, that was like the population of UC San Diego, and it seemed crowded. But imagine all 16,000 people jammed into something only like a quarter of the size. So it gets pretty crowded.
Yeah, even my high school seemed crowded. It was only like 2,000 students.
Yeah. Well, let's see who else is here. We got Moktaba and someone on YouTube named Nanya. Well, we are doing finite state machines today and learning more about how they're related to regular expressions and how to kind of switch back and forth between finite state machine and a regular expression. As we said last time, finite state machines and regular expressions are duals, which means that you can transform one into the other, and they're totally equivalent to each other. So there's nothing a finite state machine can do that a regular expression can't, and vice versa. So let's kind of jump into this. What we want to do is I'm going to show you some regular expressions, and then I want you to transform them into their equivalent finite state machines. So let's go ahead and turn this off. We'll get started on that. Okay, so as I'm reminding you about what we said last time, is that if you have three symbols all just chained together in sequence, then the way you write that out in a finite state machine is you just simply put them in a line like this. And then if you have an alternative where either you could do A or B, then you could either do that as two separate branches, or you could do two branches that go to the same state. And then finally, if you're doing the star, then you just write that as a loop. So a state that goes back to itself. So here are two regular expressions. What we might want to do is write down what languages each one of these accepts, and then from there, that might make it easier to draw the finite state machine. So let's start with the languages. What strings do each one of these accept? First one's pretty straightforward. It's just three strings. The second one is going to be an infinite number of strings, but we ought to be able to write down at least some of them. So let's start with number 1. What are the strings that this one accepts? So you can either type them in the chat, or you can say them. And as I said, there's just 3 here, so this one's pretty easy.
You're asking for the options for number 1.
Yeah.
So would it just be like A, B, X, Y, and Y?
That's good. A, B, X, Y, and Y. What about for number 2?
I guess it would be AC or B, A repeating. I don't know how to say that.
Well, we're just writing down some of the strings. So AC is one of them. BA is another.
Oh, I see.
BA, BA is another. BA, BA, BA is another. And it could also accept the empty string, because the star means it could have as few as 0 of those BAs. Okay, and then the finite state machines. Well, for number 1, you just need to make a machine that has 3 branches. So it's either going to do the AB branch or the XY branch or the Y branch. So we'll do that by writing our initial state with an arrow pointing at it. And then we've got 3 branches going away from it. One of them is the A, B branch. And then we put an accepting at the end of the B. The next one is the X, Y branch. And then finally the Y branch. So these are the kinds of finite state machines I want you to be able to draw for this particular course. This is an introduction to discrete structures, and therefore also an introduction to finite state machines, and what are also called finite state automatons. Hopefully, if you take a programming languages theory course, you'll get a more formal introduction to these. And I just want to kind of go on record to say, like, if you look on the internet or on YouTube for some examples of finite state machines, you'll see that there are some people that insist that every single state has a transition coming out of it that represents every single symbol in your language. So this one accepts A, B's, X's, and Y's. And so there needs to be an A and a B and an X and a Y coming out of each state. But in this case, if B is your first symbol, that's an error, right? That's not an acceptable string. There's no string that this machine accepts that starts with a B. And so they would say, well, you need to have a B coming out, and that needs to go to an error state. Likewise for all the others, there needs to be one for X or A and one for B. It just actually, to me, makes the diagram too complicated. And it's easier for me to say, like, any transition that's not explicitly shown is assumed to implicitly go to an error state. And that way you keep the diagram simple enough. So I'm not going to insist that there be transitions for every symbol, including ones that go to an error state. I'm not going to show the error state unless it's absolutely necessary. Okay, number 2, we want a finite state machine that has essentially 2 branches, one that accepts AC and the other one that accepts any number of BAs. So we'll get you started there. Here's a branch that accepts A and then C. But then try to figure out how to do the other branch. How can we get that other branch to accept any number of BAs, including none? I'll give you a moment to think about that one. So if you've got a drawing of it and you're on Zoom, you can maybe hold up your paper, or maybe you can verbally describe what you think it should look like. But we want some kind of branch that accepts any number of BAs.
I just drew like an empty like arrow, and then I drew like the what do you call it, the final state?
Mm-hmm. Okay,
And then I
so you
drew like
can't have
a
any
loop back
transitions that
arrow.
don't have a label on them.
Oh, okay.
All right. So all the transitions need to have a label.
Well, my thought process was like you can't make like I wanted to put like the loop back arrow on the starting node,
Mm-hmm.
but you can't make that one the final state, right?
You can. That is allowed.
Oh, okay. So then I guess it would just be the self-referencing arrow on the first node.
Mm-hmm. So how would we do the fact that this needs to accept two symbols? So I think what you're thinking is some kind of loop back here, and then that loop accepts BA, and then make this a final state. But then we need to break up this BA into two separate transitions. But that actually is fairly easy to do, right? We can just basically cut this in half, put a new state there, and then have B here and A here. Does that make sense?
Yeah, sorry, I wasn't thinking.
Okay. Now, this finite state machine, though, has a problem. It does not accept the same strings as the regular expression. This one accepts a string like BAAC. Which is not one of the strings that are accepted by the regular expression. So the problem here is this finite state machine allows us to go back to the starting state and then branch off again and go down a different branch. We need to prevent that somehow. We need to make sure that once the machine goes down that lower branch, it stays there and isn't able to go back and do a different branch. So this one is not going to work. So we need a different one. So we should still start off with AC being one of the branches. But then how do we handle that BA so that it is its own branch and doesn't allow us to go back and do the other branch?
So you're not able to have a branch that accepts an empty input?
Not yet. We'll get there, but not yet. But I can see what you're saying is like maybe there should be an epsilon branch here, one that accepts the empty string, and then some kind of cycle that goes and accepts the BA and does that. The problem with that is this is called a non-deterministic finite state automaton because you don't know whether to take the A branch or the epsilon branch without looking ahead at what symbols come next. And you want this to be a greedy algorithm where it knows which branch to take. And so these epsilons are not allowed yet. Okay? So what can we do instead? My daughter's brought over her boyfriend's dog. And so my dog is like, well, I want to play, but only for about a minute, and then I've had enough. And I'm going to hide in your room while that other dog is out there in the rest of the house. So my dog is in here hiding. The other dog is out there. Okay, so this one's a little bit tricky, but the way we do it is we will have a B branch here, and then an A branch here, and then obviously this is an accepting. And then we'll just put a cycle back, labeled B as well. Okay, so either we can do the AC branch, or we can do BA and then end, and then we can do any number of BAs. And then to handle the empty string case, we just make the initial state also an accepting state. So this one has two accepting states, one that accepts the empty string and one that accepts any number of BAs. Okay, let's go do some more. So here's two more, and again, it might be helpful to write down all of, or at least a sample of some of the strings that each one of these accepts. And then from there, draw the finite state machine. So let's work on the first one. So this one accepts like just A, which is handled by the A here, and then no B's. Now they're talking to each other. A and then a bunch of B's, maybe even A and a single B. So that's the left-hand side. And then the right-hand side is C followed by what do we got here? Any number of A's or a single B. So we could just do C by itself, or we could do CA, or CAAA, or CB, and then like that's it. So if you look at these strings here, you'll see that they're broken in kind of into two pieces. There's the strings that accept A as their first character, and there's the strings that accept C as their first character. So from there, we can see we've got a finite state machine that accepts either A or C as its first character. And then any number of B's on the A branch. So we've got B pointing back to itself and a final state there. So A followed by any number of B's, or C followed by any number of A's, or a B. Now, this finite state machine also has a problem. in that it accepts some strings that the regular expression disallows. For example, it allows CAAB, which is not allowed as one of the strings. So how do we resolve that? My dog is back again. It's like, protect me from that thing. Both dogs are about the same size, though.
Do we currently have a way to resolve this?
Yes. Like I said, every finite state machine can be turned into a regular expression, and every regular expression can be turned into a finite state machine, so there must be a way to resolve it. What you're trying to do is make sure that once the machine chooses to go down a certain branch, it sticks with that, and it's not able to return and go do a different branch. So basically the issue is right here. This loop, because it returns back to the state that it started on, it can then choose to go down a different branch.
So what I did was I made another branch for A that goes to from the current accepting state that it's looping back to another accepting state. And then I made the loop go back to that accepting state that I just put in.
Like that? Is that what you had?
Yeah, that's correct.
Yeah, so this is good. So we accept C and then any number of A's, including just 1 or 2 or 3 or 4 or none, because we've got an accepting here, or we can do the B down here. So that's good. Perfect. And then what about number 4? So we'll start with the strings that it accepts, and it accepts 3 strings, X, Y, Z, and X, Y, oh, excuse me, not X, Y, Y, X, and X, Y, X.
I think you're able to make 2 variations of this one.
What does it look like?
One's more efficient than the other one, I think.
So describe to me what one of them looks like. So we got
okay,
so the starting state.
One of them, the better one, starts with an X and a Y branching out of it. And then from those, there's a Y and an X that a Y that branches out of the X node, and then an X that branches out of the Y node.
Okay.
And then at the Y node, there's an X and a Z that branches out of that. And then there's accepting states at the end of all those.
Okay, good. So what you noticed is that two of these strings are very similar to each other. They both start with x, y. They just end with either x or z. And so that's represented in the top half of that diagram. And then the bottom half has this yx on the bottom. Essentially, what you did was you took the x, y, and factored that out and left behind an x or a z. So you kind of transformed that regular expression, although you might not have written it out yourself. Kind of in your head, you transformed that regular expression into this new one that had that common substring factored out, leaving behind only the choice. But if you hadn't do that, if you hadn't done that, and you were just kind of like, I'm just a blind robot that just simply does what I'm told to do, then you might have come up with something that looked like this. It just simply has 3 branches, but it has this unique characteristic where 2 of the branches have the same label on them. And what I like to picture is that finite state machines are kind of like, you know, exploring caves underground, or they're rooms in a house with corridors leading between the rooms, or maybe they're kind of like you know, stepping stones in a garden with paths going in between them. And so if you imagine that you're perhaps a, you know, a cave explorer like Indiana Jones, that you're in some cavern, you know, here you are, you've got your fedora on, right, you know, you got your, you know, your whip on your waist right here, and then before you are 3 doors. And one is labeled X, one is labeled Y, and one is labeled X. And you're like, huh? Which one of those do I go through? Right? My goal is to get to the accepting state. And I know that I've just received the letter X as one of the symbols that I should accept. Which one of those X doors should I go through? Without knowing what character comes next, without being able to look ahead and see what comes next. And in fact, in this particular state machine, you don't even know on the next character which one was the correct door. You got to go 2 characters ahead to figure out which was the correct door. And so that, you know, poses kind of a problem. And as you saw, one way to resolve that is simply to factor out that common substring, and then you've got a solution that doesn't involve any kind of guesswork. But if you're just a robot, if you're just a computer, and you just look at this regular expression, you go, oh, I can draw a diagram that corresponds to that regular expression. It just so happens this diagram has an ambiguous choice in it. So then the next step would be, how do we resolve that? How can we go from a finite state machine with ambiguity in it to one that doesn't have ambiguity in it? And that's kind of going to be the subject of the next week or so in this course, is how do we do that? How do we just blindly make a finite state machine from a regular expression and then transform that into something that doesn't have any ambiguities in it? Because if you were to try to make a program that represents this one, remember I did that a couple, I think it was last week, where I showed you it was just basically a loop and a bunch of if-elses. Well, the problem here is that we've got an if-else that doesn't rely on only the current symbol. It would have to look ahead at the symbols coming down later. And in this one, although we have to look ahead 2, you can imagine there might be a finite state machine where you have to look ahead 100 before you're able to finally resolve that situation. You know, that's just impossible. Not impossible, but it's impractical to write a program like that. It's particularly the way we wrote it, where it only looks at one symbol at a time, and there's no way for it to look ahead. So there is an algorithm for transforming one with ambiguity into one that doesn't have ambiguity. And we'll be looking at that over the next couple of days. So before we get to that, let's try to go the other direction. I give you a finite state machine, you write a regular expression that corresponds to it. So again, the first thing to do might be to write down strings that are accepted by both, and then see if that helps you to write down the regular expression. So looking at the first one, I can see that it accepts as little as just A. It also does A, B, C. And it does A, D. And for the second one, it can do as little as just M. Or it could do MN or MP. But every time we come back to this state, we can also make a new decision. So we could do MN and then P, MNP. We could do MPPPN. We could do a whole bunch of N's. We could do a whole bunch of P's. We could mix and match. It doesn't matter. We just got M followed by basically any sequence of N's and P's. And then finally, for the third one, we can accept X, Y, or just Y. So let's write regular expressions that accepts these strings. It's funny, on YouTube, any chat message that vaguely resembles programming languages are immediately like tagged as possible spam. And I have to go and click on show. It doesn't matter whether they're regular expressions or if they're Java code or C code, anything that vaguely resembles programming code is immediately flagged. While you're working on those, I have kind of like an interesting story about our dog. We picked up our dog from a shelter about four or 5 years ago. And you know, the shelter owners were like, we don't know what kind of dog this is. It's vaguely like a golden retriever, a little miniature version of a golden retriever. We don't have no idea. So we picked him up, and he's been a great dog, but we didn't really know what he was, just some kind of like mixed breed or something. And so just last night, I was playing with Google Lens, which is a search feature in Google where you can either take a picture of something or you can upload a picture of something, and it tells you what it is. I was doing it to identify some sea life that we had discovered along the coast of California while we were out there a couple weeks ago. So I was like, I just plugged in a picture of our dog. It's like, I wonder what it says about our dog, right? So I go to Google Lens, I select a picture of our dog, and it goes, hey, I know what that is. Let's see, that's a kokonee right there. And I'm like, you can tell that from a side picture of my dog. Surely that is just some kind of mistake. I mean, it does look like my dog here, but I mean, my dog looks like other dogs. So I go and I find another picture of my dog, more of a headshot, and it goes, oh, I know what that is. It's a kokanee. And I'm like, hey, we know what you are now. So now you're a real dog. You're not just a mixed breed like we thought you were. He's looking at me like, get me away from that other thing. It's like, there's another dog in the house. This is my house. And I'm going to show it's my house by hiding in this room. Anyway, so for the first one, we want one that accepts either A or ABC or AD. And let's see, what do we got here as far as some choices? Okay, so one of them was A, B, C, or D. And this one is pretty close. It certainly accepts A, followed by B, C, which is this middle one, and then A followed by D, which is the last one, but it does not allow that first one.
Shouldn't it be A and then or, and then in parentheses B, C, or D?
Say it again.
A and then or, and then in the parentheses B, C, or D?
No. So this one would allow either A by itself or B, C, or D. But you're close. So this does not work, and this does not work. Now, one way we could do it is just simply A or A, B, C, or AD. That would work.
That's what I wrote, but I didn't know if it was good.
That's fine. Remember, it's actually not that much different from this one right here. Just different symbols. Let's see, we could also do it as A or B, C, or D, or epsilon. Let's see, what else could we do? We could do A or A followed by B, C, or D. Remember, the or has the lowest precedence. So looking at an expression like this, this or is either the left side or the whole right side. So any one of these are acceptable. How about number 2? Certainly it's going to start with M, but then how do we handle that last bit of it?
I think it's M, N star, P star.
Close. This one is certainly M, followed by any number of N's, followed by any number of P's, but what it doesn't allow is for mixing them up, such as M, N, P, N, P, P, N.
So the N and the P should be ORed together?
Yeah. There we go. I like that one. Actually, not quite. It's closer. This one is m followed by any number of n's or any number of p's, but not like mixed up. It's either n's or p's, but not both. So some people on YouTube, I think, are suggesting better ones. Here's one that I saw, n star or p star, and then a star on the outside. So any number of n's followed by any number of p's, and then you can just keep looping back and doing that choice over and over again. You can even simplify it a little bit and do n or p star. So pick an n, pick a p, and then just keep looping back, making those choices over and over again. So you can see how when you're transforming this into a regular expression, there's like some thought that has to go on. I mean, it's important to make sure that when you come up with that regular expression, that you kind of go through and make sure that it accepts the same strings as the finite state machine did, and make sure it doesn't omit any either. And the last one seems like it ought to be pretty easy, right? It's either x, y, or y. That's it. Can we do it with the epsilons on there? You're talking about for the third one or the second one? I guess my personal opinion about epsilons is I would stay away from them if you possibly can. I mean, sometimes they're just not. It's not possible. You know, you have to put them in, but maybe it'd be possible if you possibly could. No, don't put them in. Does the third one require epsilon also? Oh, because it also accepts, yeah, you're right. You're right, this one also accepts the empty string, right? Because the initial state's also an accepting state. So here we would have to put that in, because that's kind of explicitly one of the things it accepts.
I did x or y and then in parentheses star, because then you can do 0 or as many.
Oh, but the star means you can do as many as you want, and this one either is just x, y, or just y. There's no actual loops in here, although it looks like there's.
Is there a way to do this one without epsilon?
I don't think so. Okay, so as I said before, you can draw a finite state machine that has some ambiguous choices in it. And this was the one we drew a bit earlier, where that first state has two transitions labeled x. And this is called a non-deterministic finite state automaton, or NFA. It's called non-deterministic because there's no absolute choice. There's no deterministic choice that you make at all of the states about which transition to follow. There's some choices that you might have to make. So this is in contrast with a deterministic finite state automaton, in which case there's only one transition per state to follow, right? So there's only one transition labeled X, and there's only one transition labeled Y, and there's only one transition labeled Z. So anytime you see that symbol, you know which transition to follow. But any NFA can be transformed into an equivalent DFA. Those are also duals of each other. And so this is what I want to show now, is how do you do that transformation? I think to make things a little bit easier, it helps to picture this as, well, we've got this state here where there's two possible x's coming out. Instead, picture it as one transition labeled x, but then that one goes to two places. So that's kind of like the first step, is merge those two x's into one, but then have them still go to two different states. It's kind of like being in a cave system, right? I was talking about Indiana Jones, right? Being underground, exploring these caves. And so you have a cave explorer who's sitting down there, you know, with their hard hat on, and they've got a little walkie-talkie, a little radio, this. And we got someone standing on the surface who's drawing a map, who's trying to map out what that cave system looks like. And so the person on the surface doesn't know what the person who's actually in the caves can see. And the person who's in the caves is only relaying information back to the person on the surface. So let's attempt to turn this NFA into a DFA by exploring the caves. So I've numbered all the states here as well. That'll help to kind of like keep track of which rooms, which caverns we're in. And so let's try this out. Is my cave explorer there?
Yes, there is.
Oh, she's there. Okay, so what room are you in?
Right now I'm in room 1.
You're in room number 1. All right. And what doors do you see?
Right now I see doors X and door Y.
You see an X and a Y. Great. So there's an X and a Y. So go through X and tell me. So she went through door X. Where do you end up?
I ended up in rooms 2 and 7.
Oh, okay. So 2 and 7 on X. So you're in rooms 2 and 7. What doors do you see?
I only see one door, and it's door Y.
Okay. All right, so go through Y.
I've gone through door Y.
And where'd you end up?
Right now I'm in rooms 3 and 8.
Oh, interesting. So she was in rooms 2 and 7. She went through Y, and she ended up in 3 and 8. So looking at the original diagram, we can see if you were in 2 and 7, and you walked through Y, you'd end up in 3 and 8. Okay, so you're in rooms 3 and 8. What doors do you see?
Right now I see doors X and door Z.
Oh, there's an X and a Z. Okay. So if you went through X, where would you end up?
If I go through door X, it looks like I'll end up in room 9.
Okay. And are there any doors leading out of 9?
There are no doors leading out of 9.
Ah, so I know that's an accepting state. And how about if you went through Z, where would you end up?
If I go through door Z, there's room 4.
Okay. Any doors leading out of 4?
No doors in room 4.
Okay. So that's an accepting state also. Okay, so let's go back to room number 1, and we walk through Y. Where do you end up?
I walked through door Y, and I ended up in room 5.
Okay. And then do you see any doors there?
Yes, I see see one door, and it's door X.
And where does that go?
That leads to room 6.
And then what doors do you see out of 6?
There are no doors leading out of 6.
Ah, so that must be an accepting state also. And is that all?
That is all.
Oh, thank you, my cave explorer. You've done a good job.
Welcome.
It's really as easy as that, right? All you need is someone else on the other end of a walkie-talkie. So you see how we did that? We started in room number 1 here, and then we looked to see where each of these transitions leads us. And if they lead us to 2 rooms, we kind of pretend like we're in those 2 rooms simultaneously. It's almost like you made a clone of yourself as you're exploring the caves. And so those clones end up potentially in 2, maybe 3 or 4 rooms. And then from there, they might see other transitions that leads them to other rooms. And then you explore the cave system like that. Now, when we were talking to our cave explorer and she said there were no more doors, we just assumed that those were accepting states. But really, what we do is we look on our NFA map, and any state that's an accepting in our NFA is also an accepting in our DFA. So we can see that 4 and 9 are acceptings in our NFA. So here they are acceptings in our DFA, as well as 6. And so now this NFA that we drew is the same as the one that we came up with earlier. That had no ambiguous choices in it. So here we've got a way to transform an NFA into a DFA. So let's try that again. Here we've got an NFA. We're going to turn it into the equivalent DFA by following the same process. This one I do not have a Cave Explorer for. So we're going to start in room number 1. And then we go, what transitions do we see? Well, we see an A and a B. A takes us to 2. And B takes us to 4. And then if we're in 2, thank you. She's back to the surface and she's returned my other walkie-talkie. That was my daughter. Okay, so if we're in room number 2, what do we see coming out of there? We see a B and we see an A. B goes to 3 and A goes to 4. So far, so good. Now, if we're in 4, what do we see? Take a look at our diagram. What do we see coming out of 4? Well, we know there's a B, and we know there's an A, but there's 2 A's. So B goes to 2. But where does A go? Are you able to hear me? I can see the battery in my microphone is about to die, so I'm going to replace that. You tell me where A goes coming out of 4.
would just be 3, 5.
I heard you. It said 3 and 5. That's good. So A goes to 3 and 5. Okay. So out of 3, there are no transitions. So we're done with 3. And then out of 3 and 5, let's see, I see a B and I see a B. So I know there's at least one B leading out of 3 and 5. So these B's lead to 3 and they lead back to 5. So that means that this B transition here leads back to itself. And then we're done. There are no more rooms to explore, no more transitions to follow. So to establish which are the ending states, the accepting states, you look back at your NFA and you see that 3 and 4 are labeled as being accepting. So anything with a 3 or a 4 in it is also accepting. This one's an accepting, so is this one, and this one. So anything with a 3 or a 4 in it is going to be accepting. I think this will be the last one we do. So let's start the same process over again. We're going to start in state number 1. And then which transitions do we see here? We see an A and an A. Good, so we know there's one transition coming out labeled A, but it goes to 2 and 4 at the same time. So our new state here is labeled 2, 4. And then out of 2 and 4 at the same time, what do we see? We see a B here, an A here. So we know there's a B and an A. So out of 2 and 4, B takes us to 3. B also takes us to 2. So we know this is 2, 3. So again, out of 2 and 4, there's a B that takes us to 3, and there's a B that takes us to 2. And then out of 2 and 4, there's an A that goes back to 4. Okay, I think we are done with 2 and 4. So now let's look at 2 and 3. So here's 2 and 3. I can see an A, I can see a B, I can also see a B. So I know there's an A and a B. Let's see, so A takes us to 4. And B from 2 and 3 takes us to 2 and 3. So B takes us back to ourself. And then from 4, I see a B and an A. The B takes us back to 2. So actually a new state. The B takes us to only 2. And the A out of 4 just takes us back to ourself. And then let's see, out of state number 2, I see only a B, and that only takes us to 3. So yet again, another new state. Okay, I think we're almost done. So out of 3, I see an A and a B. The B takes me back to 2. And the A takes me back to 4. And since I just went back to states I already have in there, I'm pretty much done. There's nothing new. So this state diagram, this DFA, ended up being more complicated than the NFA, a lot more states. But the acceptings are anything with a 2 or a 3 in it. So here's a 2, here's a 2, here's a 2, and also anything with a 3, which is this one, and also this one that we already circled. So that's kind of informally how to transform an NFA into a DFA. And by informally, I mean we're just looking at the diagram and we're just drawing new states. But if you were a computer doing this, you of course would not have the advantage of a nice diagram for you to follow. You'd probably have all the information contained in some kind of data structure. So that's what we're going to cover, not today, but starting on Wednesday, is how can we represent a finite state machine as a data structure of some sort, and then use that information to transform an NFA into a DFA. And that would be more similar to how a computer would actually do it. So the last thing I want to show you is kind of a simulation of finite state machines. As soon as I can find the program, I will run it. Okay, so this is an automaton or finite state machine simulator. I can put in states, and I'm going to put in one of the ones we drew early on. Like maybe I will do this one down here. This one would be labeled A, and this one is labeled C. This one is B. This is A, and B. And then this one is a final state, and so is the initial state. And if I click this little green button here, I can then type in some symbols and you can see it follow each one of the transitions. So I will do AC, which is one of the strings it accepted. Oh, I need to also mark this one as being a final state. Okay, so I can do A and then C. I can start it over again. I can do B, A, and then more BAs. Of course, I can do nothing at all, and that's accepted as well. I can do a single BA, and that's accepted. Let's see, I can maybe also do the top one that we have here. So let's see, we got 1, 2, 3, 4, 5. This one is A, and then it goes back to itself. It's kind of difficult to draw this. There's a way to... I always forget how to draw it back to itself. I just click on it. There we go. And this is B. I can move it over here. And then this one is labeled C. This one is B. This is A. And this is A. And then we got a whole bunch of accepting. So this is a final. This is a final. So is this one and this one. Okay, let's go. So we can do A, followed by as many B's as we need. We can do C, and then A, followed by as many A's as we need. And we can do C. Oops, that was not a C. We can do C, followed by B, and then we're at the end of that one. Now what about the one on the bottom? So this is not a deterministic finite state automaton. This is a non-deterministic one. So let's see if we can draw this one. So we got one initial, and then 3 follow-ons, and then 3 more follow-ons, and then 2 more follow-ons from there. So we have this one labeled X. I hope we can do this. I think we can. Get this one here, and this one is also labeled X. So we got X, Y, X on our first one, and then we have Y here, X here, and then this one is Y. And then this top one here is Z, and this bottom one is X. And this is a final, this is a final, and this is a final. Okay, so let's do it. So if I do YX, oops, that wasn't YX. Let's try that again. If I do Y and then X, it works just fine. And what happens if I do X, Y, Z? So I'm going to do X first, but you're going to see that it's going to split itself into 2. Did you see that? Let's start that over again. So if I do X, it's going to end up in these 2 states simultaneously. Then if I do Y, those 2 are going to follow over to the next 2 states. And then if I do Z, it's finally going to resolve itself, and it's just going to be the top one. And if I do X, Y, and then X again, it'll resolve itself and be just the bottom one. Here's another one that we did. Now for this one, I can't actually, this software doesn't allow me to do 2 loops, but I can do one loop that has multiple labels on it. So then I can do a single M followed by any combination of N or P. And then here's another one that we did. This one is A, this one is B. And we've got A over here, and B this way. This was B down here. That's A. This is B. This one here is A. I think that's it. Final state and final state. Okay, let's try this out. So obviously accepts A, B. A, B. You can do A, A. So that's an accepting string. Notice here that A ends up on 2 states, but one of them is an accepting, and that's good enough. So as long as you end up on an accepting, it's okay if you also end up on a non-accepting. This is still considered to be an acceptable string. What about A, B? So that is not acceptable. It did not end up on an accepting string, accepting state. If I do A again, and then B, so that was A, B, that also ends up on an accepting. How about B, B? That works. But just 2 B's does not work. How about B, A? That does work. B, A. That works as well. B, A, B. That works. A, B. That works. So I just kind of like want you to kind of have this picture or this little animation in your head that as you're going through a finite state machine, you're this little explorer hopping from room to room. And the last one I'll do is the last one we did. I think that's it. And then we had a final here and a final right here. Okay, so let's try it out. We've got A, which goes simultaneously to those two states. And so A by itself would be an accepting string because it ends up on an accepting state. Let's keep going. There's B, that's also accepting. There's B, so A, B, B is accepting in any number of B's. A, B, A is not accepting. A, B, A, and then an number of A's. Still not accepting, but then if I do a final B, it is accepting. So we had A, B, A, and then B. That works. And then any number of B's after that will also work. A, B, A, B. And then from here, we can't do any more A's, right? That doesn't work because there's no transition coming out of this top one. A, B, A, B, B, A, B. That works. So there's an infinite number of strings that this accepts. But again, I wanted you to kind of get this little animation in your head that if there's two choices, it goes through both those transitions simultaneously and ends up in two or more states. Later on, starting on Wednesday, we'll see diagrams that have possibly 3 or even 4 states that it could go to. But it's all the same concept. Okay, so that's what I had for you today. Just to review, we showed that finite state machines and regular expressions are duals of each other, and you can transform one into the other. And we also showed that there's this thing called a non-deterministic finite state automaton that has ambiguous choices in it, where you don't know which transition to follow unless you could look ahead. And we also showed there's a way to transform an NFA into a DFA, and this is true for all NFAs. All NFAs can be transformed into an equivalent DFA. Sometimes the DFA ends up being simpler, sometimes it ends up being more complicated. But any NFA can be transformed into a DFA. What we're going to see next time is two things. One is we're going to see how to represent a finite state machine, either non-deterministic or deterministic, as a data structure. We're going to do it basically as a two-dimensional matrix. And also we're going to see what happens when we throw the epsilons into it. We've avoided that up to now, but we're going to see what happens if you actually make a transition that's labeled with an epsilon. Earlier, one of the students, I think it was Max, drew a diagram or described a diagram that had an epsilon transition in it. And I said at the time, that's not allowed just yet. But we're going to see next time what happens when we do have those. What happens when we do have epsilon transitions? That actually will simplify things somewhat because it'll make it easier to turn any arbitrary regular expression into a finite state machine. If you have those epsilon transitions, it actually makes it easier to do things like isolate branches. Make sure that once the machine goes down a particular branch, it stays on that branch and can't come back. You can kind of picture those epsilon transitions as being one-way gates. Once you walk through that gate, you can't then cycle back and go back to where you were. So that's what we're going to cover on Wednesday, and probably also part of the following Monday is how to do those transformations using a data structure and involve the epsilons as well. It's a kind of a lot of information, so I'm going to spread it probably across 2 different days if I can. And then also on Wednesday, we'll have one of our last programming assignments, and this one will involve regular expressions. So we're going to learn how to do programmers' regular expressions. All we've done so far is learned about basic regular expressions. You can use the star, you can use the vertical bar, you can use the parentheses for grouping, and then that's basically it. Well, vertical bar, star, and parentheses, and that's it. Those are basic regular expressions. But programmers have a few more sets of meta characters that they can use. They can use things like brackets and question marks, pluses, curly braces. Those can all be thought of as just being shortcuts for the symbols that are in basic regular expressions. But nevertheless, your programmer's job is to be productive, and so there's more symbols for you to use. So we'll learn about programmers' regular expressions, and then one of the last assignments will be kind of like puzzles to solve. I'm going to give you some files and ask you to extract things or select things out of the files, like find all the names, find all the email addresses, zip codes, IP addresses, file names that represent just images, times, dates, anything that has a particular structure to it or a particular pattern to follow. You can probably write a regular expression to match it. So it'll be kind of like puzzle solving. I've given you these puzzles to solve, and you got to piece together the regular expressions to do it. Usually there's more than one answer, more than one regular expression that'll do it. But I think one of the kind of like the goals of the puzzle is to try to find the simplest regular expression that'll do what you want. So that'll be the final programming assignment. There won't actually be any Python programming to do. I've written the Python program for you. All you have to do is fill in the regular expressions. And then there will be one more assignment towards the end of the semester in which we put all of this stuff together. I'll have you do some problems, kind of pen and paper problems, where you're just transforming regular expressions into finite state machines, and then finite state machines, NFAs into DFAs. So we have, let's see, this is week number 13, so we've got weeks 14, 15, and 16 to come up. So probably on Monday, I'll kind of chart out what the last 3 weeks of the semester are going to look like. Once we get through with this NFA to DFA transformations, that's it for the core content of the course. Then we've got a couple of weeks where we've got some open days and we can talk about other stuff. So that is the rest of the semester in a nutshell. So I think that's it for today. We learned a lot. We learned a lot about regular expressions and finite state machines. And so the question is, will I need to be able to code as a prerequisite for the finite state machines? No, not for this particular assignment. Again, the Python program is already written for you. All you have to do is fill in the regular expressions. Okay, so I hope you all have a great day. We've reached the end of today, and I will see you on Wednesday. First, I'll say goodbye to the Zoom folks, and then I'll say goodbye to the YouTube folks. So take care. Have a great day. I'll see you on Wednesday. Bye-bye. And then YouTube folks. So you guys were quiet for a while. After one, oh gosh, that went way back to like one of the third slide or so, where someone said the final state is also an ending, or the starting state is also an ending state, and then you guys said nothing for about half an hour. So I was a little worried that you had all disappeared, but there you are again. Well, I hope you all have a great day. Thanks for watching, and we'll be back on Wednesday. And also, if you're going to watch my C programming course on Tuesdays and Thursdays, let's see, what are we doing in that course? We are, I think, answering questions about the final password cracking program, and then also starting to get into computer networking. So we'll do a Q&A first, and then, well, actually, I'll introduce the last assignment. I haven't done that yet, so we'll introduce the final password cracking assignment, answer any questions about it, and then probably start diving into computer networking. Okie doke. Again, I hope you have a great day. I'll see you either tomorrow or Wednesday. Take care. Be safe. Get some rest. See you later. Bye-bye.